Okay, here's the fourth video in chapter 3, and we'll start with combustion analysis. So this is a very specific type of problem. We've talked about combustion reactions in general, where you have this fuel, and it always reacts with oxygen gas to make CO2 and water. What we are trying to do is analyze the fuel. We're trying to figure out the empirical and the molecular formula of this fuel at the beginning. So it's something unknown. So what we kind of want to understand here is when this reacts, if all of the fuel is used, every carbon atom right here in the fuel is converted into the molecule CO2. So however much carbon was to begin with is now in CO2. All of the hydrogen that was there is now in water. Oxygen is not as clear because you had some oxygen in the fuel. You have oxygen that's interacting with it as well. And some of the oxygen is going to CO2 and some of it's going to water. So you kind of leave oxygen till last and you deal with C's and H's first because they're more clear cut. Here's an example. Methyl methacrylate, which is whatever our fuel is, has a molar mass of 100 grams. When a sample of methyl methacrylate weighing 3.14 milligrams was completely combusted, the only products formed were 6.91 milligrams of CO2 and 2.26 milligrams of water. What is methyl methacrylate's molecular formula? So here, once again, we'll focus on the carbon and the hydrogens first. So if we start with the CO2, we've got to work backwards because the amounts that we do know the original compound, but what we're really going to start with is the CO2 and the water, and you'll see why. So let's start with CO2. Here's our milligrams of CO2. Let's go ahead and get into grams first so we can use molar mass. So I'm going to divide by 1,000 to get to grams. And remember, the only thing we can do with grams is go to moles. So I'm going to take grams of CO2 and go to moles of CO2. This step is the molar mass coming from the periodic table. I'm trying to isolate carbon. So now that I'm in moles of CO2, I can make the conversion using the formula of CO2, meaning in every 1 mole of CO2, I have 1 mole of carbon present because there's only 1 carbon in the compound. So this is an important step here. 1 mole of CO2 contains 1 mole of carbon. Then I can say in each mole of carbon, there's 12.01 grams of carbon. So what I'm doing is working my way to figure out how many grams of carbon are present. And then I just convert back to milligrams because that's what the problem is working in. So I change from grams to milligrams. What you'll notice is the unit and the substance cancels out in every step here. And the whole point is just take CO2 and get all the way to carbon by himself. So what we just determined was that there was 1.89 milligrams of carbon in the CO2 produced, which means there must have been 1.89 milligrams of carbon in the original fuel, which we're trying to figure out who this mystery is. Then we use water to do the same thing for hydrogen. So we've got 2.26 milligrams of water. Let's go ahead and change to normal grams. We use molar mass to go grams to moles. And now that we're in moles of water, we can get from moles of water to moles of just hydrogen. This is where we isolate the atom. So each mole of water contains 2 moles of hydrogen. See how the formula has 2 hydrogens in it? So 1 mole of water will contain 2 moles of hydrogen. Each mole of hydrogen has a molar mass of 1.01, and then we'll convert to milligrams, and we get 0.253, which means 0.253 milligrams of hydrogen were present, and also that's how much was in the original compound. So now we can subtract to figure out how much oxygen was in the original, because remember 3.14 up here, milligrams, is the mass of the CHO fuel. So what we do is we take 3.14, which we were given, we subtract out the carbon that we just found, we subtract out the hydrogen that we just found, so that we now know how much oxygen was in the original compound. So at this point, do you see it? These 3 things right here tell me the amount of C, the amount of H, and the amount of O. Now we're back to a normal empirical formula problem, where if I start, scroll down so you can see it all, this is just like the problems before. I know the amount of carbon, the amount of hydrogen, the amount of oxygen. So what I'll do is get to moles of each of these, so then I can look for a ratio. So of course I had to do milligrams to grams first, each time. And then I could go grams to moles, grams to moles, grams to moles from the periodic table. And I get these, tiny numbers for moles. This is a correct ratio, but it's not a clear one. So what do we do again? We divide by the smallest number. So we go find the smallest, which is this 10 to the negative fifth value. So we divide by that guy every time, and we come out with a ratio of 2.5 to 4 to 1. That is the correct ratio, but we don't like this decimal, so we multiply everything by 2. So we get a 5, 8, and a 2, which is C5H8O2. And then we actually would add that up to see if it matches the molar mass, which I actually didn't do here. So if we added that guy up, we would see if his mass matched 100 grams. If it matches 100 grams, then that means that's also the molecular formula. If it came out to be 50, which it won't, it must add up to be 100. But if it added up to be 50, you would know that it needed to be multiplied by 2, for example, to get to the molecular. Okay, so here we start bouncing in between reactants and products in a balanced equation. These are called stoichiometric calculations. So remember back when we were balancing equations, we were putting coefficients, and we said these coefficients give us mole-to-mole ratios between reactants and products. So it's kind of like a recipe. It tells me how many reactants go together to make how many products. So here in B it says how many moles of oxygen gas are required to react completely with 1 mole of NO. So if we're using this balanced equation right here, you have to make sure it's balanced first, and sometimes that's your responsibility. So you always want to check. What this tells me is I could come up with several conversion factors, meaning, does it make sense that every 2 moles of NO that gets used, you would use 1 mole of O2? That's the conversion factor I made right here. Of course, it could be turned upside down as well. Another one could be for every 2 moles of NO that get used, you will make 2 moles of NO2. So you can go reactants to products and backwards. They can go upside down, but you look to these coefficients to give you the numbers. So in this exact problem, we're starting with a mole of NO, and we're trying to get to moles of O2. So what we do is we take mole of NO, the unit and the substance have to go on the bottom, so moles of NO, and we'll convert to mole of O2. And then we get mole-to-mole ratios from the coefficients. So a 2 will go in front of the NO, and a 1 will go in front of the O2. So we end up dividing by 2, and we see that you needed 0.5 moles of O2 to react with 1 mole of NO. Once again, moles are going to be kind of our middleman here. We can always go grams to moles, and we can always go moles back to grams. So here, what this big thing is saying is if you have, reactant A and reactant B, for example, you can convert in between these using that mole-to-mole ratio that we just talked about. So right here in the middle, it says use the balanced equation as a mole-to-mole ratio. You can use the coefficients to jump from any substance to another substance in a balanced equation. And then on either side, you can go moles to grams using the molar mass of whoever your substance is. So the key is that if we're starting with grams, we always have to get to moles first, and then we can convert to moles of anybody else in the balanced equation. I'll show you lots of examples here. So here's glucose reacting with oxygen to make CO2 and water. It says how many grams of water could be produced from 150 grams of glucose. Okay, so you always start with what you are given. So 150 grams of glucose is what I start with here. It's really important to write the unit and the substance. So grams of glucose are going to come down here. Remember, the only thing we can do with grams is go to moles. So no matter what the problem's asking, that's going to be your first step. Grams to moles, you use the periodic table and you add up the molar mass. That's your first step. No matter what, you're going to bring your moles of glucose to the bottom here. Remember, once you're in moles, you can jump from one substance to another. So I'm putting 1 mole of glucose on the bottom here and converting into moles of water. And to get this conversion factor, I look at the coefficients. So 1 for glucose and 6 for water. So now I have successfully jumped between substances. 6 moles of water, I can now take the unit and the substance, moles of water, and put it in the bottom. And now that I'm in moles, I can go to grams. And so I go to the periodic table to find molar mass. So what you'll notice is the first step was molar mass. This next one was using the balanced equation for mole to mole. And then we went back to molar mass. We multiply everything on the top, divide by the bottom, and we find out that you will make 90.01 grams of water whenever you use 150 grams of glucose. Okay, using the same balanced equation, this one says, how many grams of glucose would be needed to produce 200 grams of carbon dioxide? So we're starting with 200 grams of CO2. We automatically take grams and CO2 and put them in the bottom. The only thing we can do with grams is go to moles. So we use our molar mass from the periodic table and go grams to moles. Then we bring our moles of CO2 to the bottom. And once I get to moles, I'm happy because that means I can jump from whoever to whoever. So I'm leaving from moles of CO2 and I'm going to moles of glucose because the problem's asking me about glucose. I go pull the coefficients, 6 CO2 for every 1 glucose. And then I bring my moles of glucose to the bottom to cancel out. And I put my molar mass at the top, multiply the tops, divide by the bottoms, and this gives me the amount of glucose that would be needed. We continue to use these same steps, but we can kind of add to this. So a lot of reactions will have these things called limiting reactants. What a limiting reactant is the reactant present in the smallest stoichiometric amount. What that really means is it's the one who runs out first. So if at home you were making cookies and you wanted to make as many cookies as you could, your limiting reactant might be eggs because you ran out of it first. Someone else's limiting reactant might be sugar that they ran out of. So your limiting reactant is just whoever you run out of first. So for example here, if we were trying to make Oreos, which let's pretend Oreos are made of 2 chocolate cookies, we understand that, and 1 piece of icing, okay? And what you have available is 10 chocolate cookies and 2 pieces of icing. Well, think to yourself, 10 chocolate cookies could give me 5 Oreos. 2 pieces of icing could only give me 2 Oreos. So ask yourself, can I make 5 Oreos or can I actually make 2? Well, I really can only make 2 because I'm going to run out of icing. So here are some keywords. The limiting reactant, labeled LR, would be your icing because it ran out first. Your excess reactant, which I put as ER, excess reactant is who you have left over of. You have plenty of chocolate cookies. You'll have some of them left over. And then this over here, these 2 Oreos, is called your theoretical yield. It's the amount of Oreos that you should make, assuming everything goes perfectly. You know, if a piece of icing falls on the floor, then you're not going to actually make that. But that's how many you should make in a perfect world. So down here, that's kind of explained in words. Theoretical yield is the grams of product that can be made when all of the limiting reactant is used. Actual yield is the amount of product that you produce experimentally. So in a problem, you're usually calculating theoretical yield, but you have to be given the actual. You can't just come up with what the group made experimentally. That would have to be given to you in a problem. And then you can be asked to find the percent yield, which is taking your actual, what did you actually make, over your theoretical, which is what you should have made, multiplied by 100, and that will give you what's called the percent yield.